Hello, my name is Naveen. I work for Hewlett Packard Enterprise. This is a presentation about an effective blocking scheme that we designed to optimize the sparse matrix vector multiplication kernel. To provide a brief background on SpMV, SpMV is an ubiquitous sparse blast kernel. It is a very simple kernel that performs a multiplication between a sparse matrix A, which is occupied by a large number of zeros, and a dense vector X, while storing the results back into the dense vector Y. Though it is a very well-known and an important kernel for many iterative solvers, it achieves only 10% of the system peak performance. The performance bottleneck can be attributed to accessing the sparsely distributed non-zero elements in matrix A. There have been multiple hardware and software-based solutions to improve the performance. To implement these optimizations, multiple compressed sparse matrix storage representations were introduced. So these representations reduce the memory storage space and also allows us to order the non-zero elements to incorporate any software and hardware optimizations. We have shown two such popular representations here, CSR and COO. Both these representations use three different arrays to represent the sparse matrix A. So we broadly classify the sparse matrix into two different types, HPC datasets and scale-free datasets. The non-zero elements in the HPC datasets have a predictable pattern, meaning they have a uniform regular distribution. This allows the usage of hardware options like prefetching to optimize the SpMV computation. On the other end, we have the scale-free matrices where the non-zero elements are randomly or irregularly distributed. So this distribution renders all known hardware and software-based optimization solutions ineffective. So the graph here shows the performance of a sample HPC and scale-free dataset on Intel Skylake X processor using the SpMV kernel from the Intel Math kernel library. We can see that if a vendor-optimized SpMV kernel doesn't show any performance benefits on scale-free datasets, we can understand the datasets are hard to tune. So the main contribution of our work is to optimize the SpMV kernel for scale-free datasets. And we do this by introducing a new blocking solution. So for the next few slides, we will be looking at the reason for considering blocking as an optimization scheme for scale-free matrices. First, let us look at the impact of hardware prefetch. So we measured the SpMV performance with and without the hardware prefetcher enabled on Intel Skylake X processors. So the results are shown here. So the graph here shows the SpMV speedup by using hardware prefetcher against the baseline of disabling the prefetcher in different HPC as well as scale-free datasets. So from these tests, we can actually observe that prefetching is actually efficient for both HPC and scale-free datasets. But the performance impact of prefetching is more effective on HPC dataset than the scale-free datasets. And this can be attributed to the regular memory references available in the HPC datasets. In this slide, we look at the performance impact from updates in cache hierarchy in modern multi-core processors. The major change in cache hierarchy is the ratio between the L2 and the L3 cache size. We can see that the L2 cache size is increased and the L3 cache size is decreased. For example, here we have considered Intel Broadwell as an example for older processors and Intel Skylake as an example for newer Xeon processors. So here it shows Broadwell's L2 cache size being much lower than the Skylake's L2 cache size. On the other hand, we can see that Broadwell has a larger L3 cache per core when compared to Skylake's cache size. So with this information, we measured the number of L2 cache misses in HPC and scale-free matrices in both Broadwell and Skylake processors. Our expectation was that with the increase in the L2 cache, the number of cache misses should be reduced in the newer Skylake processors. And we expected this for both HPC and scale-free datasets. But we observed no such huge change in the number of cache misses. So to summarize our observation from the last two tests, we can see that there is no effect on the number of cache misses with the increase in L2 cache size. This is for both HPC and scale-free datasets. And also we observed that prefetching is not effective for scale-free datasets when compared to HPC datasets. So that the general requirement, which is to increase the reusability and improve the temporal locality for scale-free matrices, means that we can use blocking as a mechanism. And our contribution here is we introduce a new column-wise variable-sized blocking scheme and an analytical model to determine the block sizes as well. So in this slide, we are introducing our new column-wise blocking scheme. The core principle of our blocking scheme is to improve the temporal locality by trying to fit the effective working set of the SpMV computation in the cache. So in the SpMV computation, we cannot reuse the elements in matrix A. Hence, the elements are streamed into the cache for the SpMV computation, while the elements from dense vector X and Y are reusable. Hence, optimizing and increasing its reusability by determining an effective working set is important. And that has been the focus of our approach. As an example of for any column-wise blocking scheme, we use matrix A here. In simple, a column-wise block consists of a set of columns grouped together with all these rows from the matrix as part of the block. So here see that we have like two different blocks from matrix A, block 0 and block 1, where each of the blocks has like a certain group of columns and all the rows from the matrix A. So, and also we show the working set of each of those blocks. So a working set consists of three elements. One, all the non-zero elements from the matrix and the corresponding elements from the dense vector X and all the elements from the dense vector Y. So we can see that with the proposed column-wise blocking, all elements in X have the maximum reusability opportunity. Okay. And then now we can show that how to determine an effective working set. So we have used a sample matrix A with two different blocking schemes to explain our methodology to determine the effective working set. So both blocking schemes BS1 and BS2 have the same number of blocks, which is 2, but the block sizes in these schemes are different. In blocking scheme 1, we can see that we have used a constant size to determine the blocks. So we have used the block size as 4 here. So we can see block 0 and block 1 has like 4 different block columns. The problem with this approach is that we would be bringing in unnecessary elements from vector X. For example, let's say like in block 0 in this scheme, column 1 doesn't have any non-zero elements, and hence bringing in the corresponding element from the vector X is actually it's not necessary and it is inefficient. And if you look at blocking scheme 1, we have identified this issue and you have correctly avoided column 1 and column 4 and then try to bring in the next usable column, which is column 5 and its corresponding elements from the dense vector X. So essentially, this example is actually showing the core part of our approach, which is to determine the effective working set. So we use a parameter called reuse index to determine whether a given column can be part of the block. And it can be calculated by counting the number of non-zero elements in a given column. So just to brief, blocking scheme 1 depends on microarchitecture parameter like cache or register size to determine the block size. Hence, the block size is also always constant. And the blocking scheme 2 uses a reuse index to determine its block size. And incidentally, the block sizes are actually variably sized. Um, so generally, our proposed blocking approach in the previous slide is suitable for being implemented across different column-wise data formats. So for this work, we have specifically used a new column-based format called CVB, which is compressed vector blocks. So CVB is based on an existing CVR format, and it inherits the low cache miss and low pre-processing overhead along its efficient SIMD vector utilization properties from its parent, which is the CVR format. So more details on the CVR format can be available from the initial CVR paper. As an example of our CVB format, we have used a sample matrix A. So we can see that from the figure, we have provided both the CSR and CVB representation of the sample matrix A. The main properties of the CVB format is that it uses 3 different arrays similar to the CSR format to represent the matrix, where we show the value column and the row index as part of the representation. And all elements in a block are grouped together before the next block is actually used. And also it is SIMD friendly, such that each lane in a SIMD register processes independent rows at a time. So here we have created a CVB format for a matrix A with a SIMD register of 2 lanes in mind. For example, like an AVX 128 instruction set. So whenever a SIMD register actually reads an element from this matrix, say like 2 elements, each element will be placed in a separate lane, and each of those elements belongs to separate rows. For example, the first reading of A and E will have like element A from row 0 and then element E from row 1, and similar and so forth. All the elements are read in such a way that each element belongs to a different row. So more details on the CVB format are available in the explained in the paper. So in this section, we are just trying to briefly see how an analytical model can be used to determine the sizes of the block for CVB format. So while converting the CSR based matrix to a CVB based format, there are 2 basic steps involved. So the first step determines the variable sized blocks, and the step 2 uses the block sizes determined from step 1 to convert the CSR format to CVB format. So our analytical model determines the variable sized blocks, and for this, the user has to pass 2 inputs. One, the sparse matrix itself. The other one is the minimum number of columns per block that the user is expecting. So in this example, we have shown a sample matrix A with 5 columns and a user input for the minimum number of columns per block as 2. So the next step is we iterate through each column in the matrix and determine whether the column can be part of the block. We do this by checking whether the reuse index of a column is larger than the average reuse index. So if the reuse index is actually larger than average reuse index, we include the column as part of the block. We do this until the block size becomes equal to the size of the user provided minimum block size. And then we move forward to create the next block. Let's show this with an example. So for the step 1, we calculated the average reuse index. And then the next step, we start iterating through every column in the matrix. So we check whether column 0 passes the condition where the reuse index is for this column is greater than or equal to the average reuse index. Since it passes, we include this column as part of the block. And then we do the same thing for the next column, and the condition here actually fails. So we don't include this column as part of the block. And then we check whether the column has reached the minimum number of, the block has reached the minimum number of columns expected by the user. Since it hasn't reached, we move on to do this with the next column. And then again, the next column actually passes the check. So we include this column as part of the block. And at this time, the number of effective columns is actually equal to the minimum number of columns expected by the users. So we close this block and then we move on to create the next block. And we do this similarly for the remaining columns and created a separate block here. As the end of this analytical model, we can see that we have created 2 blocks and each of the both has its own number of columns. So we have provided a brief background on our blocking scheme. So let us now look at some performance benefits from our blocking scheme. So for our analysis, we used Intel Skylake X processors with 24 cores per socket. We have implemented our CVB-based variable size scheme and compiled the SpMV kernel using Intel compiler. But the problem that we faced with determining the test set is that it is hard to analytically determine the data sets that are suitable for our blocking scheme. So existing approaches like sparsity were not actually useful. So for example, let's consider matrix A1 and matrix A2, which has the same number of value for sparsity, which is basically the ratio of 0 elements to the total number of elements. And since it is same, let's say for an arbitrary cache size of 2 words, A1 takes 2 reads to do the SpMV computation because element 1 and 4 belongs to 2 separate cache reads. While for A2, it can be done with 1 single cache read. So this clearly shows that sparsity doesn't understand the non-zero distribution, and it is not suitable for identifying the scale-free matrices. And then we don't have any clear analytical model to differentiate the data set that is suitable for our blocking scheme. So we introduced a parameter called access range to identify the scale-free matrices. Access range is just the distance between 2 elements in a dense vector X, which will be gathered as input for the SpMV computation. So consider the previous example with matrix A1 and A2, where D1 is actually the access range for matrix A1 and D2 is the access range for matrix A2. And we can see that D1 is much larger than D2. And with this, we could actually extend this to the calculating average access range, which is the average across all access range values. So in this figure, we quickly show the average access range calculation in CSR format, where we use the CSR column index to calculate the average access range. So we did the similar analysis across different data sets ranging in different domains, and we saw that the average access range values for the scale-free data sets are much higher than the average access range for HPC data sets. So this could be used as a mechanism to differentiate the data set that will be suitable for our SpMV optimization mechanisms. So the rest of the slides, we quickly into different performance analysis. So initially, we set the baseline performance by comparing the non-blocking variant of CVB with CSR. The non-blocking variant just has 1 single block. So the speed up of using CVB non-blocking is actually shown. We can observe that the non-blocking variant is 1.2x times better than the standard CSR format. This can be attributed purely to the properties of the CVB that it inherited from its parent CVR format. But also, we can see that on some data sets, it wasn't showing good performance and there is a negative impact. So we analyzed the reason for this negative impact. And what we understand is that processing multiple rows is not always suitable. And specifically for data sets with a large average access range, it can have a negative impact. So the solution for the previous issue is blocking. And here we show the benefits of blocking with our variable sized blocking scheme compared against the non-blocking variant of the CVB. So we can see that because of using the variable sized blocks, we have a uniform performance benefit. And we can see that CVB provides close to 1.4x times better performance than the non-blocking variant. And also on data sets where we previously saw a performance degradation like Orkut and Pokak, we can see that there is a performance improvement. With this, we can say that large average access range data sets gets benefited from the variable sized blocking scheme. So in this slide, we quickly try to show the benefits of variable sized blocks compared against the constant sized blocks. Again, we can see that the effective working data set identification from the variable sized blocking scheme provides better benefits than the constant sized blocks. And we can see that CVB-var has like 1.2x times better speed up than CVB const. And this obviously gets attributed to the effective working set identification in our blocking scheme. And the final analysis basically compares our CVB variable sized blocking format against the highly optimized vendor-tuned Intel Math kernel library. We can observe that the variable sized blocking provides on average like 1.7x times better speed up than the highly tuned Intel Math kernel library. So which proves our analytical model determines an effective working set for a particular matrix better than an highly tuned Intel Math kernel library. So in general, our analytical model identifies the correct working set for a particular data set. For example, we have shown 3 different data sets, and each of the data sets has a different number of columns per block. And we can also see that for a particular data set like RoadNet, our analytical model correctly identifies that there is no effect in blocking, and we have just created one single block which included all the columns. So that said, there is still further chance for tuning the performance. While most data sets, the hand-tuned performance by directly looking at the average access range is almost similar to the analytical model provided average access range values. So some data sets like Amazon gets benefited, while most of the data sets are almost optimized using our analytical model. So we suggest looking at the access range for the CVB format to determine whether further tuning is required. So to conclude, we have optimized the SpMV kernel for scale-free matrices and also introduced a new parameter called access range to determine the data sets that are suitable for our optimization. And also we proposed an effective variable sized blocking solution and provided an analytical model to determine the block sizes for our proposed solution. So, and also we performed evaluation of our proposed solution using a new data format called CVB. And we could see a huge speed up both on a single and multi-threaded highly vendor-tuned against a highly vendor-tuned SpMV kernel. Also, we have provided hints for the users to further tune the blocking approach if needed. So this concludes our presentation. Thanks for listening.